You know, deep learning is pretty much everywhere. It's powering our recommendations, translating languages in real time. It's changing the world. But here's the crazy thing, the real elephant in the room. For all its power, we don't really know how it learns, not from a fundamental mathematical level. It's this massive puzzle that researchers are racing to solve, and we're about to look at a brand new piece that might just change everything.
I mean, think about it. We can build these AI models that do superhuman things, right? But what's actually going on inside? It's still a black box a lot of the time, even for the people who create them. We know that it works, but the deep why? Well, that's the big question. We're searching for the right language, the right kind of math, to finally describe what's happening under the hood.
All right, so here's our game plan for this explainer. First, we'll dig into this mathematical mystery. Then, we'll bring in geometry as the missing link. We're going to talk about the actual shape of a neural network. From there, we'll build a new geometric dictionary, look at the surprising power of something called singularities, and wrap up with why the future of AI looks, well, pretty geometric.
And look, it's not like people haven't been trying to figure this out. Researchers have thrown a ton of different kinds of math at this problem. You've got probability, information theory, even statistical mechanics and Riemannian geometry. Each one has given us a little piece of the puzzle.
But what if the biggest, most powerful tool was right there, hiding in plain sight the whole time? I'm talking about maybe the most popular field in pure mathematics, one that the machine learning world has pretty much completely ignored. Until now.
So what is it? It's called algebraic geometry. And a whole new wave of research is suggesting that this might just be the key we've been looking for, to finally unlock how deep learning really works. So what on earth is algebraic geometry? Okay, in simple terms, it's the study of shapes. But not just any shapes. We're talking about spaces and curves that are defined by polynomial equations. It's basically a way to describe really complex geometry using the language of algebra. And to really get why this is so powerful, let's compare it to something we're more familiar with. Most of us know that linear algebra is a huge deal in machine learning, right? It's all about flat spaces, lines, planes, that kind of thing. Well, algebraic geometry just blows that wide open. It's like the next level up. It lets us study these wild, curved spaces with all their twists, folds, and even places where they cross over themselves. It's the math for a non-linear world.
Okay, but why polynomials? Why are they the magic ingredient here? Well, it turns out they hit this perfect sweet spot. On one hand, they're super general. You can use them to approximate pretty much any continuous function out there. But on the other hand, they're really tractable. They're real things you can actually compute with. And that combination of flexibility and mathematical toughness is exactly what you need to get your hands around something as messy as a neural network.
Okay, so we've got our tool, algebraic geometry. Now, the big question is, how do we actually use it? Well, the very first step is to figure out the space where all this AI learning is even happening. So let's introduce a really cool new idea, the neuromanifold. I want you to picture a map. This map represents every single possible function that your neural network could ever create. Every little tweak of its internal knobs and dials creates a different point on this map. This whole landscape of possibilities. That is the neuromanifold. And this idea, it completely changes how we think about learning. All of a sudden, training an AI isn't just some abstract optimization problem. No, it's a geometric journey. The whole goal is to navigate this massive, complex, curvy map and find the one single point that best represents the real world, the ground truth.
And here's why this is such a game changer. For most models, this map of theirs lives in an infinite dimensional space. I mean, how do you even begin to work with that? You can't. But, and this is the key, if we use polynomials to build our networks, making them algebraic models, their neural manifolds suddenly exist in a finite dimensional space. And that takes a totally impossible problem and makes it something we can actually get our arms around mathematically.
So now that we have a way to describe this learning space, we can actually start to build a kind of dictionary, a way to translate all those familiar deep learning problems into the language of geometry. And this new perspective gives us this incredibly powerful new dictionary. So things we talk about all the time, like a model's capacity or how much data it needs to learn, well, that translates to the dimension and the degree. You can think of that as the curviness of its neuromanifold. Or that classic problem where different settings in a network give you the exact same output. In geometry, that has a name, identifiability. And maybe the most exciting part, all that mysterious stuff about sparsity and how networks learn features, it's all tied up in something called singularities.
The amazing thing is that this isn't just a bunch of nice ideas. It leads to real, testable predictions. For example, there's a key theorem that directly connects the geometry of the neural manifold to how much data a model needs. It basically says the sample complexity, the amount of data you need, grows linearly with the manifold's dimension, think of that as its size, and logarithmically with its degree, think of that as its curviness. This gives us a solid mathematical reason for something we kind of knew intuitively. A more complex, twisted model needs more data to figure things out.
All right, now we get to my absolute favorite part of the story. We're going to talk about the geometric flaws on our map. And it turns out these aren't bugs at all. They're actually features. In fact, they're the very things that guide the whole learning process.
So what are these flaws? They're called singularities. These are special points on the neural manifold where the geometry just gets weird. It isn't smooth anymore. Imagine a sharp corner on a cube, or the pointy tip of a cone, or even a place where a surface loops back and intersects with itself. Those are the singularities.
So why are these points so incredibly important? It all comes down to what's called a geometric bias. Picture dropping a marble onto this landscape. If it lands on a nice, smooth, flat part, the area it could roll to and settle in is tiny. The chances of it stopping right there are almost zero. But if it lands near a singularity, like a deep valley or a sharp crease, the attraction zone is huge. It's almost guaranteed to get pulled in. This means the whole learning process is naturally and powerfully biased to end up at or near one of these special singular points. They act just like magnets.
And here is the big reveal. These singular points, they aren't just some abstract math concept. On a neural network's map, the singularities correspond to simpler versions of the network. They represent states where some of the neurons have just gone dormant, they're dead or inactive. So think it through. The learning process gets pulled towards singularities, and singularities are simpler networks. Therefore, AI learning is geometrically biased to find simpler, sparser solutions. This could be the fundamental reason why networks so often learn to ignore most of their connections and rely on just a few key features.
Okay, let's actually visualize how this works. Imagine our neural manifold is shaped kind of like a cube. We start the training process right at the origin, the corner of the cube. This is the most singular point of all. It's where every single neuron is off. The network is doing absolutely nothing. And of course, the training loss is sky high.
So the network is training, chugging along, and then, bam, we see a sudden sharp drop in the loss. What just happened? Well, geometrically, our learning process just jumped from that corner point to one of the edges of the cube, a slightly less singular spot. And what does that mean in terms of the network? It means one neuron just flickered to life. Its weights grew from basically zero, and it learned its very first simple feature.
And this pattern just keeps repeating. You'll see another period of slow, steady learning, and then another jump, this time maybe from an edge to one of the flat faces of the cube. And you guessed it, another neuron activates. So, from this point of view, feature learning isn't a smooth process at all. It's a series of these discrete jumps between simple, singular structures, moving from a very basic subnetwork to a more complex one, all guided by the hidden geometry of this map.
So all of this is an incredible descriptive theory, right? It gives us this amazing new language to explain what we're already seeing. But the real dream, the ultimate goal, is to go from just describing AI to actually prescribing how we build better AI in the first place.
And that leaves us with one last really mind-bending question. If we can truly map out the geometry of learning, if we understand the dimension, the curvature, this whole landscape of singularities, could we one day work backwards? Could we actually design AI models that have a specific geometric shape we want them to have, a shape with built-in simplicity or prescribed curvature, making them more efficient and easier to understand right from the start? That is the incredible future that neural algebraic geometry is pointing towards.